Dear student, welcome back after the Eid holidays. Before Eid holidays, we have covered the concept and implementation of bee trees. We have seen how a bee tree works on, what are the benefits of using a bee tree, how we can implement a bee tree, and we have seen the insertion, deletion, and other operations from the bee tree. So I hope you will have learned the lessons uploaded before, and if you have any concerns, questions, you can talk to me or you can send me a message. Also, I would like to inform you that your projects are nearly due, so please work on the implementation of your projects so that you can get those projects completed on time. Okay, so today our topic of discussion is the graphs. Graphs basically it is another kind of data structure. When we have studied the tree data structure, we have seen that there are different traversal techniques, there are different nodes, edges, and other components of a tree. Graph is almost like a tree, but there is a minor difference, as you may remember from previous lectures. In those lectures we discussed the difference between a graph and a tree. The difference was this graph will be having a cycle, mean while traversing from one node, we can follow a path and we can return back to the same node. So that is a cycle. It means if we start at some point, we move around and come back to the same point, then it means there is a cycle exists in that particular data structure. So that was graph, and that is the only difference between a graph and a tree. So let's look at the formal definition of the graph. A data structure that consists of a set of nodes, vertices, also called the vertices, and a set of edges that relates those nodes to each other. For example, as we have seen in the case of trees, so if we look at this particular picture, we have two nodes, this one and this one, and there is a edge connecting those two nodes. If we draw another node, so again this is a graph, this is also a tree. For example, if this is the root node, so this could be a tree as well. How about if we want to make it as a graph? It is a tree as well as a graph, but if we connect this line like this one, so then it is not a tree now, but it is a graph. For example, from every node we can traverse all the nodes, and we can also come back to the same node. For example, from this node we can move to this one, and back to this one. So that is a graph. The set of edges describes the relationship among the vertices. The edges, these lines which are connecting these nodes, these describes the relationship between these nodes. For example, there could be multiple relations in these kind of nodes. Let's consider this graph as a map of a city, for example. So if we consider this as a location 1, this is location 2, this is location 3, for example LOC, location number 1, location 2, and location 3, for example. Okay, so the relationship, this edge could be shown, it could be a, for example, representing the distance between this location and this location. It could represent a cost of traveling, for example, from this node to the this node, and any other, for example. Okay, let's look at this graph, which is representing the states of a country, most probably the United States. So this is the start point, Austin. Austin may be a city, and then there are different other states: Vancouver, Denver, Chicago, Dallas, Washington, Atlanta, and so on. And there are different edges, for example, from this one to this one, this one to this one, and many others. So there is a starting point. There is also exists some cycles in this one, and nodes and edges are there to connect with each other. So this is a definition of a complete graph. So formally, if we define the graph, a graph G is defined as follows: G is equal to V comma E. So G is equal to vertices and edges. V of G is a finite non-empty set of vertices, and E of G is a set of edges, pairs of vertices. For example, the each edge will be connecting at least two nodes or vertices, V of G. So this is the mathematical definition of a graph. We can say when the edges in a graph have no direction, then the graph is called the undirected graph. For example, if we look at this particular graph, we have 4 nodes A, B, C, D in this case, and there are different edges connecting those nodes. So V of G, this graph 1, is equal to A, B, C, and D. A, B, C, and D, and E of this graph 1 will be edges, and the pair of nodes E of graph 1, it is AB, AD, and AC cannot be possible because there is no direct link, there is no edge exist between A and C. BC should be there, and then BD is there. When we when we have written the AD pair, this one, AD is this one, so explicitly DA will also be in this particular tuple. This is also called a tuple. So why? Because of this property of undirectional. It means this can be moved from this point to this point, and from this point to this point. This is a undirected graph. There is no direction. For example, if we have this kind of graph, A to B, this is a directed graph, and it means AB is different from BA. In this case, we can move from A to B, but we cannot move from B to A. In this case, because this is undirected, we can move from A to D, and also we can move from D to A. Alright. So this is the how we define a graph: directed graph and undirected graph. So when the edges in a graph have a direction, the graph is called a directed or digraph. For example, if we look at this particular graph, which is graph 2, it is a directed graph. It has edges, directed edges from each node towards some other node. For example, if we look at each node, analyze the node 1, so we have a outgoing edge this to 3, and again we have an edge from 3 to 1. It means in this case the edges tuple will be 1 comma 3 and 3 comma 1. But if we look at this point 11 to 1, so there is one direction from 11 to 1, so the tuple will be 11 comma 1, but the reverse will not be applicable in this case. So 1 comma 11 is not applicable. Similarly, if we look at this 9, so the tuple at 9 will be 9 comma 11 and 9 comma 9, because we have an edge from 9 to 9. Similarly, if we try to formulate this one from 5 to 9, so there will be a tuple from 5 comma 9 and 5 comma 7. So these are the vertices in this graph 2: 1, 3, 5, 7, 9 and 11. These are the vertices of this particular graph, and these are the edges of this graph. So we can see there is a difference between directed and non-directed graphs while making a set of vertices and edges. It is also very important in the directed graph, the order of the vertices in each edge is very important. So we can as we have seen in the previous slide, so 1 comma 3 for example is different than the 3 comma 1, but in case of undirected graph it will be having same meaning, like 1 comma 3 is explicitly meaning 3 comma 1 is also there inside. Okay, now we discussed the tree versus graphs, as we already discussed at the start of this lecture. So trees are special cases of a graph. A tree is a graph, but the reverse is not true. Means a graph might not be a tree. So in this figure we can see graph 3 is a directed graph. For example, it is starting from this point G, and then we can go to the D, I and so on. So because this has no cycle inside, it means this is a tree as well. So this is a tree as well as the graph. Okay, so if we try to identify the vertices of this graph, so we will be seeing A to J, they will be the vertices in this graph: A, B, C, D, E, F, G, H, I and J, so on. And these are the edges of this graph. Because this is a directed graph, so we have to carefully extract the edges from this graph: E to D, E to I, I to H, I to I comma J and so on. So all the tuples, we identify those tuples and we draw those tuples. So this will be the set of vertices and edges for this particular directed graph. There are some terminologies which are called the graph terminologies. We will discuss those one by one. One is the adjacent nodes. Two nodes are the adjacent nodes if they are connected by an edge. For example, if we look at this part of this graph, some bigger graph, so 5 is adjacent to 7, means 7 is approachable from 5, or in other words we can say that we can move from 5 to 7 with this particular edge. And similarly we can say it as 7 is adjacent from 5. This 7 is adjacent from 5, means 7 is approachable from 5. In this case we cannot say that 7 is adjacent to 5. Why? Because there is no path or there is no edge exist from 7 to 5. So it means we cannot say that the 7 is adjacent to 5. Okay, if it could be undirected graph, then we can say that 5 is adjacent to 7 and also 7 is adjacent to 5. But in this case it is the one way direction, so we can only say 5 is adjacent to 7, but the reverse is not true. Next terminology is the path, a sequence of vertices that connects two nodes in a graph. That is called a graph path. For example, if we look at this graph, short graph, there are 3 nodes. From this to this, if there is a path, so these edges will be included in the path from this node to particular this node. So a sequence of vertices that connect two nodes in the graph. For example, if we are interested to connect this node number 1 and node number 3, so these will be the edges which are connecting 1 to 3. So that will be a path from 1 to 3. Complete graph, a graph in which every vertex is directly connected to every other vertex. So if that is the case, we will say that it is a complete graph. For example, if we have 5 nodes and every node is reachable by the other node, or in other words, we can say if there is a path from every node to every other node in the graph, then it is a complete graph. Okay, this is the example of a complete directed graph. We have a graph here in this picture. We consisting of 4 nodes, and there are different edges connecting each node. So we have a path from every node to every other node. For example, if we randomly pick A and D, we can see A is adjacent to D and D is adjacent to A. Similarly, if we pick the C, so C is also reachable to A, also reachable to B, also reachable to D, and same true for B and D. For all the nodes, we have a path from every node to every other node of the graph. So that is the definition of a complete graph. So what is the minimum number of edges in a complete directed graph with n vertices? It will be equal to n cross n minus 1, and this is the complexity of n square of this particular kind of graph. So here the n are the vertices, n represents the vertices, and the total number of edges can be calculated with this formula, n into n minus 1. For example, here n we have n is equal to 4, so 4 multiply by 3. So the number of edges will be 3 in this particular completed graph. 12. 4 into 3, 12. So 2, 4, 6, 8, 10 and 12. 2, 4, 6, 8, 10. This has been connected twice, so we will consider this as a single, and this one is 12. So 2, 4, 6, 8, 10 and 12. So in complete directed graph, if we have n number of vertices, we can check how many edges will be there with this formula, n into n minus 1. Okay, look at this undirected graph. What is the number of edges in a complete undirected graph with n vertices? So it can be calculated with this formula, n into n minus 1 divided by 2. So if we look at this graph, it is having 5 nodes, and we have a path from every node to every other node. For example, j to k, j to l, j to m, j to n, n to l, m, j and k, and so on. So this, because of the directionless of this particular graph, we can conclude that the formula will be n into n minus 1 divided by 2. Divided by 2 is because this single line is covering the 2 lines in case of a directed graph. So if we look at this, there are 5 nodes. So 5 into 5 minus 1, which is 4. 5 into 4, 20. 20 by 2 is equal to 10. So there will be a 10 edges which are connecting these 5 nodes. Similarly, if we have say 20 nodes, so the number of edges will be how many? According to this formula, this you have to this is a very easy question. You have to reply it in the WhatsApp discussion. If we have 20 nodes, alright, so how many edges will be there in case of a directed graph and in case of an undirected graph? Okay, this is the weighted graph example, a graph in which each edge carries a value. For example, if we analyze this particular graph, Aston, Dallas, the graph which we have seen in the previous slides, now it has some values on the top of edges. For example, Austin to Dallas is 200, Dallas to Aston is 200 again. Similarly, this one is 800, this one is 800. So these are having some values, some connection with these nodes. Let's say we suppose that this is representing the distance from one destination to other destination. For example, Aston to Dallas is 200, for example, kilometers. Similarly, from Dallas to Aston is again 200 kilometers. And the road is both way, the double road from Aston to Dallas and then from Dallas to Aston. Similarly, if we look at this node Aston to Houston, so there is a value of 160. It means from Aston to Houston there is a distance of 160 kilometer, but there is no road from Houston to Aston. Mean this is a single road which is going from Aston to Houston. Okay, so if we analyze this graph, and what you have to do is you have to draw this graph on the paper and send me the adjacency matrix, like which one is adjacent to which one. The one I can do for you, that is Austin is adjacent to Houston, Houston is adjacent from Austin. So similarly you have to do for rest of the nodes. So we will continue from this point to onward. So meanwhile you can have an idea of graph, its terminologies, its weights and so on. So thank you very much and Allah Hafiz.